My name is Stelios Mamagkakis, and I'm representing Samsung Semiconductor. And today I'm going to present how to enable IoT and M2M applications and wearables in particular. So I'm going to start with who we are and what we do. Then I'm going to focus on the devices themselves, then on the implications that they have on the cloud, and then finally to go over the opportunities for the chips that Samsung Semiconductor produces to enable all these devices. So you probably all know Samsung Electronics, and this is the mother company of Samsung Semiconductor. You know it from the TVs, from the mobile phones, but I'm actually not going to talk about this from a consumer side. I'm going to talk about it from a business to business side and about the chips that are inside it and enable it, and what actually Samsung Semiconductor produces, which is a portfolio mainly of memory and system LSI products, where from system LSI we have application processors, modems, security solutions like smart card, image sensors, as well as dedicated bioprocessors. And here I would like to mention that Samsung Semiconductor is actually the second biggest semiconductor company in the world after Intel, where the main focus is memory, where in DRAM we're #1 in volume for more than the last 20 years. And in respect with storage, we're also #1 in flash for more than the last 10 years. So today I'm going to present from the perspective of the chip, and then more particular from the memory side. And then I'm going also to show the innovations that are coming into this space that enable IoT and M2M applications. So starting with an overview of the wearables market, being also in the wearables track today, there we are going to see an explosion in devices. What we project is that by 2019, we are going to have more than 120 million units being produced every year. And this is something that is going to come from a variety of vendors and for a variety of applications. Today, we already see a lot of these applications already in the marketplace, like glasses, watches, wristbands, also smart fabrics, as well as other applications like special buttons or rings. And what is very important to note is the variety of all these applications and many more to come. But then also some common factors. One common factor is that all these actually are very small. They do not have a lot of space for the semiconductor components which are inside. And then, of course, that they are mobile. So you carry them with you. They have a battery inside. So therefore, also, power consumption is very important. So this power consumption is what influences the battery life, and it's one of the key things that also drives the semiconductor component technology behind it to enable these applications. There, I would like to focus on the packaging for the semiconductor. There we see a clear winner in respect with packaging form factors, and this is the EPOP, package-on-package solutions, where actually, as you see, instead of having an application processor, eMMC storage, and mobile DRAM next to each other on the board, there the main solution which is going to be provided, and is provided already today for wearables as well as IoT applications, it is going to be a package including both storage and DRAM on top of the application processor. So this is a solution that brings up to 60% savings in the form factor, in the area that is needed. And then very importantly, it can lead to also very thin systems, up to 1.4 millimeters for a Samsung solution being used. And then also as an implication of the memory consumption constraints, there we also, as shown in the previous slide, in respect with storage, we have a clear a winning solution, which is eMMC. And then in respect with memory, mobile DRAM is the one that is going to be used. And more in particular, low power DDR3 and low power DDR4, which can bring savings from LPDDR2 to LPDR3 10% in power consumption. But then very big improvements we can see in the usage of eMMC when compared with other solutions like hard drives or SSDs, which of course also have form factors which are much bigger. So these two things, power consumption and form factor, are key, and we see as common denominator in all semiconductor designs. One of the things which is not a clear winner today is what comes in respect with connectivity. So there we see a variety of solutions having different trade-offs in range, bandwidth, as well as power consumption. So from Bluetooth, Zigbee, Bluetooth Low Energy, all the .11x standards, as well as going from 2G to 4G, LTE, advanced LTE. So there, depending, of course, on the application that is being used, we see that either one of those connectivity standards, or in many cases, multiple connectivity standards would need to be enabled on the semiconductor component that drives this wearable IoT or M2M application. And even more so in respect with computation, as well as the size of the actual storage and memory, there we also see a very big variety. So depending on the needs of the applications, we go from a solution. Here you see the Arctic family of Samsung. You can go from a solution that is as low as 80 megahertz to dual core to as much as an octa-core running at 1.3 gigahertz. So in the same way as with connectivity, here also for computation, we do not see yet these mass applications, these mass usage of one specific usage, which will drive only one type of processor, connectivity and chip from the semiconductor domain. But then we see that the market actually would need to provide a whole range of solutions, both in respect with the actual storage, as well as the computation and the connectivity. And taking this actually one step further, what we see from our side, from the semiconductor side, we see big implications in respect with IoT, wearable M2M devices, also to the cloud. And this was already mentioned. And when there is not enough computation power on the device itself, so when you want to move even beyond this range of computation, then what do? You actually go and you store the data that cannot be stored on the device, or you process the data when you don't have enough processing power, not on the device, but then you go and you process it on the cloud. So here is a very simple example. When you have your smartwatch and you want to tell to your car, please turn the air conditioning on, or in a few years from now, park the car or bring the car from the parking, then what actually happens is that your voice is recorded. This data of your voice is sent over to Google or to whomever. Then it is processed on the cloud. Voice recognition does this in the cloud, and then it sends back either to the car or your device that yes, it has been acknowledged, your command is going to be executed. So basically, we see that what this means is that from all these explosions in devices, we also have an explosion in respect with data. And the data which on the one hand side is stored, and there we see going from 4.4 zettabytes today to what we think is going to be 44 zettabytes of information in 2020. And then also all this information that is going to be stored in the cloud, coming from IoT, M2M, wearables applications, all this also is going to be processed, and actually also moving to up to 35% of the data, of this data will actually be processed, like the example that I said with the voice recognition. And what this means, the processing of this data means, is a lot of use of in-memory computing. And there we see basically also an explosion in respect with the density of the memory that is in servers today. And there we see also a growth of about 26% over the next years. And this is what also drives the processing. And on the other hand side, we also see an explosion in respect with the hot data that is being stored in these servers in the cloud. So when you give your command, you don't want to have your voice recognition after 5 minutes, you want to have it instantly. And this means that also from a storage perspective, you want the fastest solution possible. So there what we see also is a lot of movement towards flash storage, and there we see, of course, the SSD, the solid-state drive solution, having a really huge growth, up to 51% year over year the coming years. And there, of course, is also where the small chips are having a big impact, chips that also Samsung Semiconductor produces. And there I'm also going to show some innovations that also help in this space to meet the requirements of the user for increased density, faster performance, power efficiency, as well as increased reliability. And there what we see as one driver driving energy consumption down, but then also performance up, is actually moving from one technology node to the next one, so shrinking. And there we see actually the impact going down to 20 nanometers with the DDR4. There we see also the impact, especially on power consumption, being huge. And probably today, most of the servers in the cloud which process all this information coming from IoT are at DDR3 at 2x nanometers. And there we can see that by utilizing the latest technology, you can actually save up to 40% in respect with power consumption, and also as a result, have a reduction in your total operation cost and total cost of ownership, which then also has an impact on the business model of all these IoT applications, which then also need the cloud in the background to process the data. And then, as mentioned before, what also is very much needed is a higher and higher density of memory in order to be able to process this data as fast as possible. But then one of the problems that we have when we actually, as we do today, stack more and more wafers inside a memory chip with a conventional wire bonding solution. There we have the problem that actually we meet performance boundaries, and there Samsung's solution is actually the innovative TSV through silicon via, where you see that actually there is a via going through the different stacks in the chip, and this basically enables to have higher density memory and with at the same time being able to have the performance needed as well as the power consumption needed. And the 3D TSV technology is something that Samsung first has introduced. And there you see that we are able to drive these high memory density applications, not only at the same performance and the same power consumption, but even improving on that. And there you see an example of a proof of concept system that we had with Lenovo and SAP, where we actually improved up to 1/3 the power consumption, and then in another POC that we had with Atos and Bull in particular, where we even managed to increase the bandwidth by 1/3. And then finally, in respect with storage, as mentioned before, what we see is the evolution from hard disk drives to SSD, where you can achieve performance 5 times higher, and then in that way be able to enable from the cloud in real time what is going on in the back of all your IoT and wearable applications, and then moving also from HDD to SSD, you have also really a very dramatic reduction in power consumption, leading to almost 14-15 times power consumption reduction. And there also in this domain, we have innovation improvements in respect with speed. And there we see that also today the NVMe SSDs can provide actually 4 times the performance of what today is conventionally being used, which is the SAS SSDs. And finally there, in order also to accommodate for all this explosion in storage, another innovation from Samsung is vertical NAND, which goes into these SSD drives. And there compared with, comparing the vertical with the planar NAND, there you can see actually that by stacking 48 layers and more, actually as technology improves, you are going to see the stacking even reaching double as much. You can improve density by 2 times, also having 50 times less power consumption, and also 10 times more endurance. So also vertical NAND is an innovation from Samsung that ahead of our competition we bring in front. So to conclude my talk, what we see in the IoT space, but also as an implication of wearables and M2M, is we see as what is driving this is low power and a small size. On the one hand side. On the other hand side, there is not yet a conclusion in respect with connectivity. Neither there is one application yet which is going to define the processing and storage needs. So therefore, the chips which come out, which are addressing this space, are going to be low power, small form factor, and then they're going to have a flexibility when it comes to connectivity solutions, storage, and performance. And then when you do not have enough on the device itself, what is going to happen is that you are going to utilize the storage and performance that you can get from the cloud using your wireless connectivity. And basically what we see as an implication of that, an explosion of data in the cloud, and also the processing needs to analyze and give meaningful feedback back to your device. So there, what we see as an impact is, from the chip side, is that we would need more and more high density in memory computing, and then also for hot data that the storage is moving towards flash. And with that, I would like to conclude my talk, and coming from a Samsung Semiconductor, indicate once more that small chips for enabling IoT and M2M applications have actually a big impact. Thank you.
Forgive me if I missed it while I was making notes, but were you touching at all on energy harvesting? I'd love to know about the future of that in the short term.
Yes. Actually, no, in this presentation, I wasn't touching upon it. Neither there is today an energy harvesting solution being offered by Samsung Semiconductor. But having a bit of a background in this space, the technology today is not efficient enough in order to drive the power needs of the processors that we see today in IoT and M2M applications. Perhaps when you have only what is called intelligent dust or just sensors, there you will be able to power these sensors with such harvesting mechanism, but not a device that you can carry yourself. This would be too little power.
Too little, yeah. So another hope dashed, but certainly something for further work. Stylianos, thank you very much for your time.
Thank you.